In this video, we study about the continuous random variable and its cumulative distribution function and the probability density function. We know that a continuous random variable can take on any value in the observation interval. And a good example is a noise voltage. Suppose if I draw noise voltage something like this, then at any given instant of time, it has got some value. And if you go for any other instant, it has got some other value. So it takes on continuous values. Suppose here this value is somewhere 2.37. Immediately after that, it may have the value something like that 3.2.2378. So theoretically, the range of values is infinity. It can take on any value from minus infinity to plus infinity. Cumulative distribution function, CDF. The concept of CDF is same for both discrete and continuous random variables. So it is defined as the probability that the random variable x takes the value small x. So it is indicated as capital F x x. X denotes the random variable. X is the value that the random variable takes. So basically it is defined as the probability that the random variable x takes the value less than or equal to x. So it is the probability at a given point x. Now we observe the properties of CDF. As we have defined, CDF is the probability that the random variable x takes on values less than or equal to some small x. So therefore, being a probability, its value always lies between 0 and 1. This is clear. The second one is that CDF is a monotone non-decreasing function. What is meant by that? Suppose if x1 is less than x2, then the CDF at x1 is less than or equal to CDF at x2. This gives us the concept of monotone non-decreasing function. Probability density function, PDF. For discrete random variables, for DRV, we have seen PMF, that is probability mass function. For continuous random variables, we take PDF, that is probability density function. What is probability density function? Once you know the cumulative distribution function of random variable, then if you differentiate CDF, you get probability density function. As the name suggests, PDF indicates the probability between any 2 points. Suppose this is the PDF curve, it gives us the probability of a random variable lying in the interval A and B. That's why it is known as PDF. So the PDF is obtained by differentiating the CDF. Now it is indicated with small f x x. This small x indicates the value and the capital X indicates the random variable. So therefore CDF is obtained again from the PDF. How it is obtained? CDF is given as probability of x less than or equal to x. It means from minus infinity to x, what is the probability? Therefore, this value is obtained by integrating the PDF between minus infinity and x. And it is also evident from this equation. Suppose if you integrate this equation on both sides, we have integral fx x dx that is equal to fxx. It is obtained from this equation. If I integrate this particular equation, then we get this. So therefore, two important equations are here. One is by differentiating CDF we get PDF, and by integrating PDF between minus infinity and x we get CDF. Both these concepts of cumulative distribution function and probability density function are very much essential to understand continuous random variable. We discuss some properties of PDF. We have seen that the PDF, just I draw here, the PDF is nothing but the probability of any random variable lying in the interval A and B. Suppose here in this diagram, between A and B, what is the probability? This is itself is PDF. That is the meaning of PDF, probability density function. It gives the probability of a random variable lying between the interval A and B. Now, the PDF, as it is giving the probability between the interval A and B, it is always greater than or equal to 0. It is a non-negative number or a positive number. Secondly, the total area under this curve is always unity. Again, being the probability, the total area occupied by PDF between the intervals minus infinity to infinity is 1. Because minus infinity to infinity under PDF is nothing but probability of x lying between minus infinity and infinity. So it is 1. Therefore, the PDF is a non-negative function and its total area is 1. And one more important point is the PDF at the same point on the curve, if a particular point, if I consider, the PDF is 0. Why so? Suppose if we want probability at x is equal to x, I am taking only a single point. And if we substitute in the equation, the limits would become now from x to x. Between the same limits, the PDF is 0. Therefore, for any continuous random variable at a single point, the PDF is 0. We have different types of PDFs. One type of PDF is uniform PDF. Uniform PDF is that it has got PDF that is constant or available, that is uniform between given interval like I given here. At this point, the PDF is uniform. As shown in the diagram, this PDF is uniform between A and B. This is known as uniform PDF. It means it is uniformly distributed over the interval A and B. So mathematically how we define? Between, say, the variable value is x less than or equal to A, the value is 0. Between A and B, its value is 1 by B minus A, and beyond B, its value is 0. This is how we define PDF, that is uniform PDF. We can compute this value 1 by B minus A. We know that the area under this is 1. In that case, it has to be 1 by B minus A. So therefore, this is the uniform PDF. We compute the cumulative distribution function from the uniform PDF. I redraw the diagram here. I redraw the diagram of uniform PDF for the sake of explanation. So between A and B, the fxx is uniform. This is uniform PDF. For this, we want to compute CDF. We know the definition of CDF. By integrating the given PDF between minus infinity to x, we can obtain fxx. Therefore, how we write this? Fxx is equal to integral minus infinity to x. As we know that below a, this value is 0. So we can put the limits as a to x. And between a and b, the value of random variable is, as per PDF definition, it is 1 by b minus a. We can refer the definition of PDF in that it is given between a and b, its value is 1 by b minus a. So by substituting that and solve this equation, I will get the CDF between A and B as x minus A by B minus A. Below A, as it is 0. Above B, it is 0. So this is how we are computing cumulative distribution function from the given uniform PDF. So in the previous example, from the uniform PDF, we computed CDF. Now we are drawn the diagrams of uniform PDF here. This is the PDF for the uniform PDF, which is uniform over the interval A and B that we have seen for PDF. From this, we derived CDF. So by integrating fxx, by integrating the fxx between say minus infinity to x, we got the CDF fxx. So we computed that, and this is the diagram for CDF. So from signals and system, we can verify that if you integrate a rectangular function, you get a ramp function between A and B. So for the given uniform PDF, you get the CDF as a ramp function between A and B. So in this video, we started with CRV, and then we defined the cumulative distribution function. From the cumulative distribution function, we understood how to derive the probability density function, and we considered one example of PDF, that is uniform PDF, and computed CDF from the given uniform PDF.